So this is lesson 6.3b, going a little deeper into our study of logarithmic equations. Today we'll be solving some basic equations, but they will require some strategies. 3 different strategies, in fact. So our instructional objective today is you will use the proper log properties to solve log equations, and you can use domain restrictions to eliminate extraneous solutions. Okay, so extraneous means extra that they're no good. You have to throw them out. Okay, so if you weren't remembering what extraneous means, it means that they're false solutions, so you can't use them. And we will be using domain restrictions to do that. So what I'm going to do is just do a little reminder over here on the left-hand side of the note page. Well, actually, I'm going to do it right here in these 2 empty blank spaces, but don't write that down in those spaces because we're going to write the log properties there. I think you just need to pay attention to this, and that'll be enough of a review. If you recall yesterday, when we introduced the logarithms, I told you that logarithms, or we talked about logarithms being the inverse of exponentials. We did. So when we solve an exponential, remember, you're not writing in these spaces right now, you're just watching. If I have 5 to the x power equals y, okay, is my domain restricted? Or can I pick any x I want? Any x I want, right? So I know that my domain is absolutely unrestricted. X can be anything. However, what do I know about my range? It's restricted to what values? Can't be 0. You can't make an exponent equal 0. I mean, well, you can't make a base raised to an exponent equal 0. It's not just 1 to infinity. Can't I approach 0? Yeah, it's open from 0, so it's approaching 0. So I can get really small positive values, but I can't get 0. So we would graph -1 up 1/5, 0 up 1, and then 1 up 5, and we would graph our exponential equation with your horizontal asymptote y equals 0. So you can approach it, but you can't get there. And then we talked about logarithms being the inverse, which means their x's and y's switch. So if I say this, the log of base 5, same base, of x equals y, well, what that really means, that's difficult to graph. But if I convert it, it means 5 to the y equals x, right? Convert. So you see what happened? The x's and y's switched. So that means that the domains and ranges also switch. So the domain of a logarithm, this guy right here, x, cannot be 0 and it cannot be negative. It has to be positive values, tiny positives to ginormous positives. The range, however, will be unrestricted. So if I were to graph this, what I would do, guys, is I would pick values for y. I'd pick -1, 0, and 1. And 5 to the -1 is 1/5, and 5 to the 0 is 1, and 5 to the 1 is 5. And so you can see what happens with my points. Remember that this point over here was -1, 1/5. Over here, it's 1/5, -1. So if that's 1, 1/5 would be like right here, and your graph point would be right there. And then 1, 0, and then 5, 1, which is way over there off the screen. But the graph does that. And the horizontal asymptote becomes the vertical asymptote. So when we're solving log equations, the thing that we have to be concerned about is what are the domain restrictions? Okay, so let's talk about some log properties, and then we'll come back and talk a little bit more about that. So here we go. Log properties. Start with this statement for all 8 properties. It says this: if, I'm just defining, it's a formal definition. If B m and n are positive, and b does not equal 0, because your base can't, 1, so positive numbers and not 1, then these properties exist for all logarithms, and there are 8 of them, and we have to employ them when we're solving logarithmic equations. And you can either understand them or you can memorize them, one or the other, or maybe both. The first one we talked about yesterday. If we have the log of some base b of 1, our solution will always be 0. Why? Because b to the 0 equals 1. Right? We do your little conversion. So anytime you have the log of 1, it's 0. The log of 1 is 0. The log of 1 is 0. The log of 1 is 0. Tattoo it on your brain. Don't tattoo it on your body, okay? All right, next one. Log base b of b is always, so if the log and the base are the same and they fit our definition, it's always 1. Why? Because b to the 1 equals b. If you do the conversion to the exponential form, you can see why that's always going to be true. Right? The next one, we did do a little bit with this one yesterday as well. If we have log base b of b to the x power, the answer will always be x. Why? Convert. B to the x equals b to the x. You can see it when you do the conversion to exponential. Okay, P.S. These are not log properties. Those are exponential equations. They're just explanations of the log properties. I think they help you understand them better. Last one is this. Base b to the log base b of x. So that's an exponential, but it contains a log, equals x. Well, that's an exponential, and it's hard to see. But if you convert it to a logarithm, put the base back in the basement, right? Log, put the base back in the basement, and these two things switch sides. Log b, base b of x equals the exponent, log base b of x. True statement. So those 4 log properties, you're pretty much expected to memorize those or know those. Notice when the base and the base are the same, that the exponents are the same. Because remember that this is an exponent when you're in a log. Yeah? 2 bases, 2 exponents. If the bases match, then the exponents match. Okay? All right. Now, here are 2 other properties. We won't be using properties 5 or 6 today, but I am going to introduce them right now. So here we go. This next property says, if I have the log base b of the product, log m n. So I'm multiplying the log of m and the log of n together. Sometimes it's really difficult to solve equations like that. So it's true that if I'm multiplying logs, that I can separate them. That the log of a product is equal to the sum of the logs if you separate them. The log of a product is equal to the sum of the logs. Now, I wonder if you could tell me what you think the next property is going to be. The division. You got it. Yep. So the log of a quotient, division, the log of a quotient is equal to the difference of the logs. And if you recall last year, if you had me in math analysis, you guys wrote proofs. And you'd say, I used property 6. I used property 7. Oh my gosh, you even had matching activities. Okay, these last two we are going to employ often today. This first one I like to call power up and power down. And it looks like this. The log base b of m to the power p, and remember p can be anything I want, the log of a power is equal to the power times the log. So that's power down, bring the power down, or you can take the power and put it back up in the power position. It's a nice little rule because sometimes you want to get that exponent down out of the way. So the log of a power equals the power times the log. This last one, you employ often. The log base b of m is equal to the log base b of n. If the logs are equal, then the numbers are equal. Basically, if they match same logs, same base, just drop the logs, solve the rest. So we will employ those two properties today. So we have three different types of questions that you have to answer, and you have to employ a different strategy for each one. So this one is the strategy for a log equals a log. Okay? So when you have an equation that has a log equals a log, this is a strategy that you can use. But let's read the instructions. It says, use the log properties to solve for x, indicate the properties you used, and checks for extraneous solutions. So I'm actually going to have you start by finding the domain restrictions for these logarithms. Because remember when we graphed, logarithms have domain restrictions. So here's what you have to do. We have to, I'm going to put this information up here in this space. Okay? The log of a negative does not exist. The log of 0 does not exist. And so anytime we create like the log of -2, well, that doesn't exist. So we have to throw it out. So if we can identify what quantities we can use for x, then we can solve our equation quickly. It's easy to solve the equation, and we can see if the x is in our domain or not. So here's how I go about this. I say, okay, so this x right here, this log, has to be greater than 0. It has to be positive. It can't be 0. It can't be negative. So maybe at first, I start out on a graph saying x has to be greater than 0. Has to be. So I'm talking about this part of my graph. Domain restricted to x is greater than 0. But it also has to be true for the other side. So I'm looking for the restriction here. And you have to be careful. You can't just find the 0 and go, okay, then it's greater than 0. Be really careful. That's a negative x. That reverses everything. So 8 minus x also has to be greater than 0. So what's the restriction there? Well, if I bring that over there, right, that says 8 is greater than x, which means x is less than 8 if you reverse that statement so that you can use this arrow to tell you which indicate which direction you go. Less than 8 is going that way. So you are restricted in the domain because it has to be true for both of them. So the domain, you have to find it first. That's supposed to be an 8. I keep turning my 8s on their sides and writing infinity. So we are stuck in the open interval between 0 and 8. So if our x is anything outside that domain, it's extraneous. So let's go and solve this equation now. So I'm going to pick up my pencil, and here I'm going to employ property 8 because I have the log of 4 equals the log of 4. I have that. So if the logs are equal, then the numbers are equal. I can just drop the logs and solve the equation. So that's 2x equals 8. Divide by 2, x equals 4. And then I just have to make sure that that's in my domain. Can x equal 4? Yep, so I'm going to write is in the domain and this is my expectation for your homework, that you write a justification. Therefore, x equals 4 is your solution. I expect to see that statement. In fact, you can just write x minus 4 in domain. You can skip the word is. I get it. Okay? So find the domain. Restrictions first. Let's look at this next one. So here we have 2 log base 5s equal to each other. So we can solve those. But first, let's find our restrictions. In this case, x minus 2 has to be greater than 0. This cannot be 0. This cannot be negative. So x has to be greater than 2. Do you agree? So if I were to throw that on a number line real quick, it would look like I'm going that direction. Okay, so greater than 2. But I also have to find the domain restriction here because I have to go with the most restrictive environment. It has to be true for both of them. So we have 3x plus 7 also has to be greater than 0. Or 3x has to be greater than negative 7. Or finally, x has to be greater than negative 7/3, which is to the left of that, right? But it's greater than. So what's true for both of them? What's my domain? It has to be true for both of them. Open from 2 to infinity is correct. So we're looking for, it has to be true for both of them in order for there to be an answer. So now we can go, you know what, I forgot something. I said to indicate the property used. Pause. What property did we use? 8. So just write property 8. All right, so what property am I about to employ again? Property 8 says if the logs are equal, then the numbers are equal. And then I can just solve that up. So subtract 3x to this side, add 2 to that side. We get negative 2x equals 9, and x equals negative 9/2. And then you ask yourself, is that possible? Is it in my domain? It is not in the domain. Therefore, no solution. No solution. That situation does not exist. Questions about that? Okay, last one. Now, this one's a little trickier because you're going to have a quadratic inequality, and you got to use sign charts for those. Or you have to remember the rules. So, x squared is greater than 0 means I'm looking for all numbers squared, that I'm looking for positive numbers for my x's. That's what I'm looking for, right? Positives are greater than zeros, right? So, well, what's the 0 of x squared? 0. So if I do just a really quick little sign chart, and I take x squared, and I say, all right, to the left of 0, what kind of response do I get? Plug in a negative 1. Negative 1 squared is positive. Plug in a positive 1. Positive. So when you have a quadratic, you have to remember that. When you have a quantity squared, the answer is either 0 or it's positive. So, well, unless it's like a negative x squared, then you got to watch out for that. But, so in this one, our domain so far is everything but 0. I can have all the x's that I want except for 0. But then I have this restriction as well to consider. So we'll do negative 3x minus 2 is greater than 0. And we'll solve that real quick. And we'll be on alert here. Add 2 to both sides. We're getting ready to divide by a negative, which means we have to do what with our inequality? That's right. Less than negative 2/3. Don't forget when you do that. So that's here. So I'm wondering, where do these two overlap? Where's the most restricted domain? Exactly. It's just that section. None of this works for the second. So your domain is from negative infinity to negative 2/3. Okay, so we're stuck. Our x has to be in that section. But we can still apply property 8, correct? So we're going to use property 8 to say x squared is equal to negative 3x minus 2. And since it's a quadratic, we need to find its zeros to solve it. So add 3x, add 2. X squared plus 3x plus 2 equals 0. And of course, you can factor, use quadratic formula. I think factoring would be much faster, right? Yeah. X plus 2, x plus 1. So your zeros are negative 2 and negative 1. Now let's check them. Are they in your domain? Yep, there's negative 1 right there, and there's negative 2 right there. So in domain, therefore, x equals negative 2 and negative 1. Negative 1. Let me get a negative. So those are the properties. That property 8 is really good for when you have a log equals a log. Just remember to look for your domain restrictions. Okay? Then we have some other strategies to employ. Okay, so this set of problems is different. Now in your homework instructions, it'll just give you a whole mess of different types of problems and say solve the equation. That's all it says. Here's the strategy you're going to employ when you have a log equals a number. When you have a log on one side and a number on the other side, if you want to solve this equation, you need to convert to an exponential. You do. But it's a logarithm, which means it has a domain restriction. So first you find it. But at least you only have to find one domain restriction per problem instead of both. So what's our domain restriction here? X minus 4 has to be greater than 0. So our domain is 4 to infinity, open interval. So a little bit easier, less work. Convert. This problem should be pretty easy to see. 3 squared equals x minus 4 converted to the exponential, right? 9 equals x minus 4. So 13 equals x. And then you just check it. Is it in your domain? Yep. 13 is definitely in the domain. Therefore, x equals 13 is your solution. So it goes a little faster, a little easier to manage. Questions? Okay. Domain. Restriction. X has to be greater than 0. So our domain is 0 to infinity. And we convert. So 9 to the 3/2 equals x. Now some of you might be really tempted to get out your calculator and have your calculator do your thinking for you. Your calculus teacher's not going to wait for you to plug that in your calculator. You should be able to do that pretty much immediately by yourself. So just if you need a reminder, when you're raising a base to a fractional exponent, the denominator is the root of the base and the numerator is the power. So if we were to convert that, that's like saying the square root of 9 cubed. And you can decide whether or not you want to do the square root first or the cube first, because square roots and powers have the same power, so you can do whichever one you want to do first. They're inverses of each other, so it doesn't matter. So what do you want to do? 3 cubed or the square root of 729? You want to do the square root of 729? Or 3 times 3 times 3? I think 3 cubed is easier to do versus the square root of 729. They're the same, but I don't want to cube 9 first and then find the square root of that. So 27 equals x. Makes sense? So just a little reminder how to do this. Okay. Is it in my domain? Yep. Is in domain. Therefore, x equals 27 is your solution. Last one for this type of problem. Okay, we've already done this. We already know this domain restriction. What's the domain? That's the zero's a restriction, right? Everything but 0. Remember we did that before. We did the little sign chart. I don't want to do it again. So it's everything but 0. There's our domain. And then we convert. So what's our base? So we have e to the negative 2 equals x squared. And we want to solve for x. Well, it's a quadratic, right? So I either have to factor or employ the square root property or use a quadratic formula. I think I'd like to use a square root property. And I'm going to convert left to right, right to left. And I'm going to write e to the negative 2 with a positive exponent. 1 over e squared. And here's my reasoning. I'm going to square root that x. So I want it to be easy to take the square root of the other side. So that's x is equal to plus or minus square root of 1 over e squared, which I can simplify. 2, positive or negative. Square root of 1 is 1. Square root of e squared is e. And here's what I know. I know 1 over e is about 0.37 because we talked about that the other day. So this is about negative 1.37 and 0.37. So negative 1 over e is in this side of your domain. Positive 1 over e is in that side of your domain. So in domain, therefore, x equals plus or minus 1 over e. I would like the exact answer, not the approximate answer. We use approximates when we graph. Or unless if I ask you to do approximates. Okay, questions? All right, last one. So here we have an exponential, but it does contain a log, which means it has a domain restriction. But, so over here, this is the problem. The x is in the exponent, which makes it difficult to solve if I can't make each side have the same base. Can I make 9 base e? I can't. So I have to employ a different strategy if I can't do that. So here's what I'm going to do. Convert. So let's find our domain restriction. What is x? What is our domain? Has to be greater than 0, so 0 to infinity open. Okay, good job. So we have to consider that because we have a logarithm in our equation. And then let's convert. So drop the base into the basement. So natural log, right? Do I put an e? No. Of 9 equals 2 natural logs of x. Now at this point, what I would like to do is drop the logs and say if a log equals a log, then the number equals a number. But this is a problem. This says the log equals a number times a log. But do you recognize this? What can I do? I can use property 7, power up. A number times a log is the same as the log raised to that number's power. They're the same. So we have the natural log of 9 equals the natural log of x squared, and that is property 7, which we need to indicate because it says so. Now, can I employ property 8? I can. If the logs are equal, then the numbers are the same. Square root both sides. X equals plus or minus 3. Then we check our solutions. What do you think? Negative 3 is not in the domain. In domain. Therefore, x equals 3 is the only solution because the negative 3, let me do this. X equals negative 3 is not in the domain. And so sometimes you get to keep one answer and you have to throw the extraneous one out. And so there's 3 different strategies that you're going to employ using your log properties and your ability to convert back and forth between exponentials and logs. Your homework is on Canvas for homework 6.3. You're doing 18 through 32 even, because we've already just done most of the odds together. So you should be able to look at your notes and work your way through these problems. I think if anything's going to mess you up, it's going to be your domains. So be really careful.